Hi, this is problem 1315. So we are solving problems for chapter 13, which is kinetics, relating force and acceleration. And so I will read the data that is given for this problem. So we have a disk of 3 kilograms that is attached to a cord, as you see here, and the cord is attached to a ball and socket, so to the center of this big platform, right? So the platform rotates very quickly when I place the small disk. So the small disk, let's write that, starts from rest. Little disk, right? And this platform is moving very quickly. So if you stand up in the platform, right, you see that even though the disk is accelerating to catch up with the acceleration of the platform, because you have a friction that is dragging the disk is moving slower, right? Okay, so and then they ask us to find the time that requires the disk to accelerate. So it will be accelerated till it catches up with the velocity of the platform. But before that, the cord will break. And they said, how much is the time that requires the disk to accelerate until the cord breaks? And the maximum tension that the cord can sustain is 100 newtons. We always start our solution by doing the free body diagram and the kinetic diagram. We know these two. We will make them equal to do our equations of motion. So we do our disk, right? And first of all, in order to do our free body diagram and our kinetic diagram, we want to select which type of coordinates we will use. Since this is moving in a circular path, I will use tangent, normal, and vertical coordinate system. So here I will use a normal, tangent, and vertical, and here too, right? My normal, my tangent, and my... So which forces do I have in my free body diagram? Okay, I have my weight, and the weight of the disk is mass times gravity, and the mass is given, which is 3 kilograms, so this is 3 times 9.81. Then I have the normal force of the disk, let's call it normal D. And then we have, for the relative velocity, is moving in that direction because it still hasn't catch up with the disk. So it's moving that direction, so the friction opposite to the motion, and then I have also the tension of the cord. So I have 4 forces in this diagram. And in this diagram, I have my mass times tangent acceleration, and here I have my mass times normal acceleration. We know that this is mass times the derivative of the velocity, and this is mass times velocity squared over radius of curvature. And the radius of curvature is given, and the mass is given. The velocity is not given, and the acceleration is not given either. So now that we have our free body diagram and the kinetic diagram, we apply our equations of motion. As you know, this is force equals mass times acceleration, being this a vector equation. And since we chose to use normal and tangent coordinates, so we will add forces. My normal direction, we have the tension, and we don't have anything else, equals to mass times normal acceleration. Velocity squared over radius of curvature. In my forces in the tangent, I will have friction force, and I don't have anything else, equals to my mass and tangent, which is mass times velocity dot. And in my vertical direction, I have weight, right, negative, plus normal of the disk. And here I can say that the normal of the disk force will be equals to mass times gravity, and mass is given, which is 3, gravity is given, which is 9.81. So we have the normal, and we are given the kinetic coefficient of friction to find our friction force. Our friction force, we know that is kinetic coefficient of kinetic friction times normal. And this is equals to 0.1 times 3 times 9.81 friction. Solving the system of equation now. Which actually is very easy friction, because from here we have the friction force, so we can get the acceleration. So let's name this equation 1, this equation 2, and this equation 3. From 2, we get that the friction force, which we already calculated, 0.1, 3, 9.81 is equals to the mass times the 8 points. This is actually, let me substitute this mass that we have, 3. And from here we get that the acceleration, or the derivative of the velocity, is equals to 0.819. This mass goes, okay, so it's 0.1 meters over second square. So this is the first value that we get. And then, so we use this equation, and from equation 1, we know that we want to go to the limit to be able to find that velocity, right? So the velocity that we will reach is for 100 newtons is equals to the mass velocity square over radius of curvature. So we can substitute the mass, which is 3, and we can substitute the radius of curvature, which is 1, right? Here we can get the velocity, and actually, well, it's just the square root of 100 divided by 3, right? And that's 5.77 meters over second. Okay, once we have the velocity and the accelerations, so it requires time. Now we do a kinematic analysis. And we know that acceleration is the derivative of the velocity, right? Therefore, the acceleration derivative of time is equals to the derivative. So I integrate those. This is 0 to time, and this is velocity 0 to velocity final. So from here I get that the acceleration, which is this part over here, as you see, only depends on the coefficient of kinetic friction and the gravity, so this is a constant. Since this acceleration is constant, I can say that this is time equals velocity final minus velocity initial. And we see that the initial velocity is 0 because they tell us that it comes from rest. And then I get that time is equals final velocity, which is the one that I found, over acceleration. So time is equals to final velocity, which is 577 over 0.810. Therefore, time is equals to 5.896. And that's the answer of the problem, because that's what we were looking for, time when it reaches the maximum tension of the core.